Welcome back, statistics students. Now that we have learned about indices of central tendency and variability, we will now cover how to change the scales of our score distributions via linear transformations. So what is a linear transformation? Simply put, it means we will transform all of the scores on our current scale of measurement and put them onto a new scale. The term linear transformation means that if we were to represent the scores as a graph, the new values would be represented as a straight line. But why would we want to transform our scores in the first place? Aren't our original scores enough for analysis? Perhaps they are, but there are pertinent reasons for transformation. Suppose you noticed a constant error across all of your scores. You can use linear transformation to easily fix your scores. A more common use of linear transformation, however, is to place the scores on a more interpretable metric. Sometimes your score values are very large or complex, making direct analysis rather annoying. You can use linear transformation to rescale those values into something easier to work with. Similarly, if you believe your current score scale is hard to make sense out of, you can instead transform the score to something easier to interpret, such as the method of standardized entrance exams, such as the ACT or the GRE. The formula for a linear transformation is rather simple. To get a new transformed score y, you will first multiply your x value by a coefficient, henceforth referred to as b. We then add a constant value, known as a, to complete the transformation. Note that you can also divide x by a number, in which case b will be represented as a fraction or a decimal. Similarly, to subtract a value, we would make a negative value. If we are not adding or subtracting anything, a is equal to 0, and there will be no plus or minus present after x. Likewise, if we are not multiplying or dividing x by anything, b is equal to 1, and you'll see x by itself. Let's practice some basic linear transformations. Suppose we want to multiply each value by 2, then add 3. Thus, y equals 2x plus 3. All we need to do to find our new value is to plug a number in for x. Let's try x equals 15. That means y equals 2 times 15, then plus 3. 2 times 15 is 30, and 30 plus 3 equals 33. Likewise, if x equals 2.3, then y equals 2 times 2.3 plus 3, which equals 4.6 plus 3, which equals 7.6. As mentioned earlier, linear transformations also work with division and subtraction. For example, let's say the transformed value y is x over 2 minus 12. This is the same as y equals 0.5x minus 12. If x happens to be 20, then y equals 1/2 of 20 minus 12. That will give us negative 2. Similarly, if x equals 100, then y equals half of 100, which is 50, then minus 12, which is 38. Sometimes you might see a linear transformation where you are to add or subtract first, then multiply or divide. For example, here we have a transformation where, by order of operations, we are to add 3 first, then multiply the result by 3. You can most certainly transform in this order. If x equals 10, then first we'll add 3, giving us 13. We then multiply 13 by 3 to give us 39. Of course, you can always transform the transformation itself with a little algebra, turning it into the more familiar form by distributing the coefficient to both terms, giving us y equals 3x plus 9. Plugging x into this equation gives us 3 times 10 plus 9, which gives us 30 plus 9, or 39. Those are the basics of linear transformation. Now let's discuss what happens to various aspects of our distribution when it is transformed. Let's start with indices of central tendency. The mean is actually the most important index of central tendency when discussing linear transformation, as will be discussed in future sections. For now, it is important to remember that the mean is itself a score in its distribution. Therefore, we just treat the mean as any other score and transform it as usual. Likewise, the mode, median, all relevant percentiles and quartiles can be transformed to the new distribution in the same manner. Let's practice this. Suppose our transformation is y equals 4x minus 1. If our original mean was 30, then our transformed mean should be 4 times 30 minus 1, which gives us 120 minus 1, or 119. If our original 90th percentile was 11, then our new 90th percentile would be 4 times 11 minus 1, for 44 minus 1, or 43. Ultimately, central tendency transformation is rather straightforward. But what about variability? Unlike with mean, median, and the like, indices of variability are not values on the scale of scores. Rather, they're more of a function of how wide-reaching our data is. The constant of a linear transformation merely shifts the location of the distribution. Therefore, the a value of a linear transformation does nothing to variability. The b value, however, does affect variability. For semi-interquartile range, you must multiply the old q value by the absolute value of b to get the new semi-interquartile range. We use the absolute value because q is by definition positive. For variance, we take the original variance and multiply it by the squared value of b to get the transformed variance. This means that the transformed standard deviation is simply the original standard deviation multiplied by the absolute value of b, exactly as q was. Again, the standard deviation must be positive. Let's practice this. If y equals 7x plus 2, and the semi-interquartile range of x is 5, then the semi-interquartile range of y is 7 times 5, or 35. If the standard deviation of x is 0.3, then similarly, the standard deviation of y is 7 times 0.3, which gives us 2.1. Now, if the transformation was instead y equals negative 7x plus 2, the absolute value rule still means we are multiplying 5 by 7, not negative 7. We still get a transformed semi-interquartile range of 35. Likewise, the transformed standard deviation is the absolute value of negative 7, or just 7, times 0.3 for 2.1 once again. Finally, it is important to discuss what happens to the shape of your distribution when you apply a linear transformation, or rather, what doesn't happen. In most cases, there will be no change to the shape. No matter what value b and a might be, the modality will never change. Also, as long as b is positive, the skewness will remain intact. The only exception is when b is negative. A positively skewed distribution will become negatively skewed if b is negative, and vice versa. However, perfectly symmetrical distributions will stay symmetrical despite this negative b value. Now that we have learned how to use transformation equations, let's think about these transformations in the opposite manner. Suppose that rather than wanting to find new scores using a given formula, we want to instead redefine our distribution to a new set of values, usually a mean and standard deviation. Therefore, if we work algebraically, we can define the transformation values of b and a, given our original distribution, and the new scale which we want to transform to. To find our coefficient b, we can take the new standard deviation we want and divide it by our original standard deviation. By the way, if you want a negative b value, just make b negative. To find our constant a, we'll take that b value we found, multiply it by our original mean, then subtract that product from the new mean that we want. Time to practice. Let's say that our original distribution had a mean of 48 and a standard deviation of 12. Now, suppose we want to condense that to a distribution with a mean of 5 and a standard deviation of 3. Therefore, b would equal our new standard deviation of 3 divided by our old standard deviation of 12, which gives us 1/4 or 0.25. Now, a should equal our new mean of 5 minus 1/4 of our old mean of 48, which is 5 minus 12, or negative 7. Thus, our transformation formula is 0.25x, or 1/4 of x, minus 7. While these types of transformation are useful for creating new scales, perhaps the most useful application of linear transformation is to put our scores onto a standardized scale. This is, in fact, the most common type of transformation. We often refer to this style of standardization as the z-score. For the standardized distribution, aka the z-distribution, we define the distribution as having a mean of 0 and a standard deviation of 1. In terms of b and a, b would equal 1, our new standard deviation, divided by our old standard deviation. A would then equal 0, the new mean, minus our old mean divided by the old standard deviation. A would then equal 0, the new mean, minus our old mean divided by the old standard deviation. Putting those together, we eventually get our most common z formula, which is to take our original x score, subtract the original mean, and then divide this difference by the old standard deviation. This will give us a value that tells us how many standard deviation values a certain score is from the mean of our distribution. Let's give this a whirl. If we have a distribution where the mean is 30 and the standard deviation is 6, and we want to find a z-score for an x value of 39, then z is equal to 39 minus 30, which is 9, divided by 6, which is 1.5. That means that a value of 39 in this distribution is 1.5 standard deviations above the mean. If our score was 24, on the other hand, then our z-score is 24 minus 30 all over 6, which ultimately gives us negative 2/3. Much like the transformations themselves, z-scores work in reverse. That is, if we are given a z-score, we can find the x value attached to it. To do that, we can just algebraically alter our z-score formula. That is, x should be equal to our given z-score multiplied by the standard deviation of x plus the mean. Let's practice one last time. Let's suppose we have a distribution of scores where the mean is 50 and the standard deviation is 8. Also, let's say we want to find the score that has a z-score of 2. That is, we want the x value that is 2 whole standard deviations above the mean. Therefore, x is equal to 2 times 8, which is 16, plus 50, which gives us 66. Likewise, if we want the z-score of negative 0.75, or the score which is 3/4 of a standard deviation below the mean, then x will be negative 0.75 times 8 plus 50, which is the same as 50 minus 6, which is 44. To summarize, this section is all about taking our old values and transforming them onto a new scale. We learned how to use these transformation formulas, how to calculate these formulas when we have a transformed distribution in mind, what happens to our distribution's identity when it is transformed, and we learned about standardized scores, also known as z-scores, which will be a very important concept for all future sections of this course. Until those future sections, thank you for watching, and may all of your analyses be free of error.